Good morning, good afternoon, or good evening, wherever you are. Thank you for making AP Human Geography a part of your day. We're just going to jump right in here with Chapter 1, Thinking Geographically, Key Issue 1, How do geographers describe where things are? So let's jump right into the content and understand where we are in relation to what the College Board's goals for us are. This unit, right? Chapter 1, Thinking Geographically, also corresponds to the College Board's Unit 1, Thinking Geographically, for AP Human Geography. It is going to weigh about 8 to 10% for your AP exam. That's rather significant, by the way. So the following are some of the main concepts that we'll be going over in the next 4 key issues that make up Chapter 1 under the umbrella of Unit 1. Hoping this makes sense, and it definitely will the more we review and discuss it. So here are our objectives for the day. We're going to explain the differences between early maps and contemporary maps. We're going to describe the role of map scale projection, and also we'll look at the process of making maps both historically and currently. We'll look at how latitude and longitude are used to locate points on the surface of the earth, and then we'll at the end talk about GI science and remote sensing, GPS, GIS, things of that nature, with the transfer goal of understanding how all this content relates to your world. Okay, here we go. Let's define geography. A fellow by the name of Eratosthenes kind of coins this term. More on him here in a second. But if we want to get into kind of the etymology of the term geography, geo means earth and graphy means to write. So like writing down the earth is essentially what that means. The basic questions we will always come back to every single unit are where and why. Where is this particular activity located, and why is it located there? Chapter 2, population. Where is the world's population, and why is it there? Chapter 3, migration. Where are people moving to, and why are they moving there? Where are people moving away from? Why are they moving away from there? And we could just keep going on down the line. Geography is kind of unique in that regard because we're asking where and why questions, and we can actually via GPS or remote sensing or physical travel move to different places currently, right here, right now. We can examine different places of the world and evaluate what's going on, where and why, right? History is a little bit different. A historian asks 2 questions for the most part, and that's when and why. And, outside of a couple sci-fi movies, we can't time travel. That's not a thing. Okay, so the historian is a little bit limited and is kind of stuck in the present, whereas the geographer is not stuck on Earth's surface. They can move. So we got to talk about maps. Your book has hundreds. That's not hyperbole. That's a fact. Hundreds of maps. Well, what is a map? You can read it's right there. A map is a scale model of real world, small enough for practical purposes. When I think of map, I think of my children like to watch a show. It's called Dora the Explorer, right? And there's a map guy that's always on there. He's like the old school map, right? When they come out with like the Dora, the new school Dora, the map kind of changes, and there's some global positioning systems there, GPS, if you will. Cartography will be the science of making maps. Now, the old school map makers, they did the old, geo, earth, graphy to write. They used to have to sit down and write that out. Modern day map makers use satellite imagery and computers to make that work for them. More on that, and I'll show you some examples of that here shortly. So there's really 2 purposes that a map serves. There's kind of the old school purpose, and I'm an old school guy. I'm an old soul, I have been told. And that is to simply identify location, whether absolute or relative. Let me give you an example of absolute location. If I say that Southport High School is located at 971 East Banter Road, Indianapolis, Indiana, 46227. That is absolute location, my friend. Or I can give the coordinates, the latitude and longitude, if you will. But if I say Southport High School is located across from Perry Stadium on the west side of Shelby, right? In between Banta and Southport. That is relative location. There's a difference. Relative is in relation to another thing. Absolute is the absolute location, the pinpoint. Now, that's the old school way that we use maps as kind of a reference tool. It can also be used as a communications tool. And by that I mean this. It can tell you a story. It can tell you what's going on. We can evaluate trends. We can look at physical features. We can look at geographic phenomena. More on that here in a second. Here's the old school way. You know, when I was a kid, we'd go on a road trip, and there was a thing called a seat back. They still have those, actually, by the way. But always in that seat back was a copy of the Ram McNally Road Atlas. And my dad would be like, "Hey, son, get back there and open that atlas and tell me where I need to go. Where do I need to make a left or a right?" We don't do that too terribly much anymore. If you are doing that, there's a couple new inventions that we can help you out with that are going to facilitate better travel on the road. So that's the old essential way, right? We're showing geographic features, we're showing the locations of places, and it gives absolute location, okay? The new way we're using maps, particularly, you know, I'm talking second half of the 20th century and beyond, we're using it to communicate information. This map right here is a map of the world, but it's showing farmers per square kilometer, okay? That is something that you will come to know later on in chapter 2 as agricultural density. So we're seeing where there's a lot of farmers per square mile, and there's a few number of farmers per square mile. Quick question, just to kind of get the ball rolling. I'm not going to answer it right now. I'll let you wrestle with it. If you want to be economically developed, do you want a lot of farmers per square mile in your society, or a few number of farmers per square mile in your society? That's a good question. Go ahead and wrestle with it. So this right here is a map of DC, the District of Columbia, Washington, DC. And it's a map, it shows using census data of median or middle household income. What we see is, will you tell me what we see? I see pockets of poverty. I see pockets of wealth and affluence, and I see some middle class. Now, how we might come to define those might differ on the individual, but you can argue about what the numbers are, okay? The numbers are given right here, and we're simply evaluating where wealth is concentrated in DC. So going back to the dude that was the first to use the word geography. He invented it, right? An ancient Greek scholar by the name of Eratosthenes. Why do you need to know this guy's name? Because he shows up on almost every single AP exam. So just know his name. You know, he's got a kind of a cool haircut. Next time I go to Great Clips, I might ask for the Eratosthenes. It's pretty slick, actually. This is somebody who you definitely need to know. Now, we could talk about Ptolemy. We could talk about the age of exploration. We could talk about dudes like, you know, I don't know, Magellan or Columbus. Essentially, once you get to that age of exploration, the 1500s, the 1600s, if you want to know anything about Magellan, he was a Portuguese explorer. He was the first European to cross the Pacific Ocean that we have on record. Columbus, you know, he was an Italian guy. Both these guys were working in Spanish explorations. He crossed the Atlantic Ocean, I believe, 4 times. Map making became really important to those guys because they were leaving, and they weren't leaving for like 5 minutes. They were leaving for extended amounts of time, and they kind of needed to know where they were going. Some of them set out to go in particular places and found that they didn't end up even where they were trying to go. So we, you know, as humankind are working through the process of accurate map making really in the 16th, 17th centuries, working through that process. Here was the map by Eratosthenes, by the way. If you want to check this thing out, like, okay, I get, if you can follow the mouse here, he's got a little spot for Ireland, got a little spot for for Britain, yeah. Not much in terms of Scandinavia, Norway, Sweden, Finland, those dudes around. Libya makes up a third of the world, evidently, right? Which is not accurate, obviously. And the rest of North Africa or the rest of the African continent is kind of like exempt here. We got Asia, India, not much here in terms of, Oceania or, New Zealand, Australia. Those guys are out, obviously. South America, North America are out on this map, but all things considered, 194 BC, question mark, pretty good job, I'm saying. I mean, maybe I'm an easy grader, but flash forward to the 16th century, and now all of a sudden we start getting a more comprehensive view of the world. Again, inaccurate, yes. Better, absolutely. And that's kind of been the process. I want to show you a few places where you can get to some contemporary maps. And I just picked 3 random ones. The first one is this metrocosm.com. Again, these would be maps for a reference tool. Same thing. Sometimes you can catch decent cartographers on Twitter, and sometimes you can catch some decent things on the Google. Let's go first to the how we share the world one. Okay. Now here you got a map of the world, but you can manipulate it. There we go. You can manipulate it by, if you want to, gross domestic product or debt, population, births, things of that nature, but you can only do one at a time. That's kind of limited. I wonder if you can do more than one. Answer yes, and I'll get to that here at the very end. Here's just the guy on Twitter. His name's Max Galka. I'm not responsible for all the beliefs of these individuals, but there's several guys. Conrad Hackett's another guy to check it out. Simon Kierthmeyer is another guy you can check out on Twitter. But you check out, they've got different maps that you can then begin to use, again, as a reference tool, as a communication tool, rather. And then here's another one, Google Maps Mania. They've always got cool stuff, so I can look at this. But okay, let's check this out. Here's a map of the German road accident map. Okay, let's check out what's going on. We can see where accidents are, and then based on that, you can kind of make informed decisions as policymakers or citizens about ways to alleviate those traffic issues, whether it be congestion or accidents, things of that nature. I'm not going to get into German, traffic accidents because that's just not really my thing. If it's yours, head to googlemassmania.blogspot.com and you can have all of those accidents at your disposal. Okay, let's flash forward on to map scale. All right. You got to put like a scale on a map, okay? We define map scale as the relationship of a feature, of the size of a feature on a map to its actual size on Earth. The basic idea then of the map scale is, as you're bringing something to scale, you are, I'm trying to think the best way to word this. Let's provide a little bit more context to that here on the next slide. There's essentially 3 ways to present map scale. The first is written, where you literally just write it out. It would be like this bullet point A here, right? 1 inch equals 25,000 miles. That could be a way where you could do it. If you wanted to put that in a fraction scale, 1 over 25,000, that will work. And if you want to do it on a graphic scale, I'm sure you've seen some of these before where you measure this out. And then, it kind of gives you. Now, if you got a really nice detailed map, they'll give you all 3. So it's not super complex or anything. I don't know why some maps don't give you all 3. Like you're right there. You've made the map. You put 2 of them down. Just go ahead and put the 3rd down. But, sometimes there's a war on a graphic scale for whatever reason. So looking ahead of that, let me just give you an example. Now, this is a map of the state, not Washington, D.C., the state of Washington. Go up to the Pacific Northwest, right? So right next to Oregon there, and then we'll have California on the Pacific coast. So the very first thing it gives us that I care about, I'm looking at the scale. So I see 1 to 10 million, okay? Zoom in from that, and I get a regional map, and now I'm 1 to a million. And I zoom into that, right? And I'm getting a map of downtown Seattle, and I'm 1 to 100,000. And then I zoom into that, and notice I got I got a graphic scale on all these as well. And now I'm 1 to 10,000. Okay. Let me ask you something. If I was going to break this down and say which has the smallest scale and which has the largest scale, what would you say? Of the 4 pictures presented, which would you say has the smallest scale and which would you say has the largest scale? This is a bit counterintuitive because you might say, oh, 10 million, that's got to be the largest scale. Actually, that is inaccurate. The large scale map is the 1 to 10,000, excuse me. The smallest scale represented here is the 1 to 10 million. Would you rather have 1/10,000,000th of the world's wealth or 1/10,000th of the world's wealth? You would obviously rather have 1/10,000th. That is a larger number. It's a larger fraction. So large scale maps represent smaller areas and small scale maps represent larger areas. The smallest scale map you're going to have is a map of the world. All right. So we have to project these maps because Earth is darn near a sphere. And so accurately representing what's on a globe is really hard to do when you're putting it on a piece of paper. A globe even, like I would love to be able to issue you guys, like we have 200 some maps. I can't issue you 200 globes, right? It wouldn't fit in your locker. Do you even use lockers anymore? That's not going to work. So there's going to be distortion when you take a spherical thing and you put it on a flat map. Translation, maps lie. Every map lies. Oh, not the map I like. I use a project. No. They lie, okay? Because they have to. Because when you put a spherical object onto a flat piece of paper, you're not going to do it perfectly ever. Here's some of the ways that maps can lie to you. Let's use the word distorted, all right? They can lie in terms of shape. So sometimes certain areas on a map are going to be larger than they actually are on Earth's surface. They can lie in terms of distance. The distance from 2 points could be bigger or smaller based upon the projection of the map. They can lie in terms of relative size, and they can lie in terms of direction, right? So size and shape are kind of similar in that regard, right? When you start getting in terms of direction, like that might actually be important if you're like a seafaring individual out there on the ocean, right? So, there is no perfect way to do this. They all lie. That's a fact. Let's look at a couple. Let's look at 3 examples and what's going on. The first is the Mercator projection. You say, oh man, that's nowhere close. Like look at Antarctica. Yeah. Oh, look at Greenland. That's unfair. No, it's really not. This is mostly for seafaring activity. The basic idea of the Mercator projection is where it matters most, shape is distorted very little. But the relative size is grossly distorted at the poles, and that is a bummer, okay? It's not the one I would ever use. I actually don't mind using the Robinson projection, although it's come under a lot of attack recently in the last 25 years or so. The Robinson projection is useful for displaying information across the oceans. Does it get the size wrong, the relative size? Absolutely, particularly at the poles, but not only at the poles. A criticism is that it's kind of Eurocentric in nature. But then the equal area projection one, this one right here, okay? This is mostly what your book uses all throughout. The equal area is nice because the main benefit is that the relative sizes of land masses on the map are the same as they actually are in reality. Okay. Let's get to something you probably know of, but we have to make sure that we review and shore up our skills. Meridians and parallels, right? Meridians are lines of longitude, and parallels are lines of latitude. Meridians, again, are the ones that go north and south. Think of Meridian the road, 135. It goes north and south. The prime meridian is located at 0 degrees longitude in Greenwich, England. I'll give you more of the history on that here in a second. But whereas latitudes, again, those are basically evaluating your distance in relation to the equator, right? Okay, so latitude and longitude, they can be used to identify absolute location, obviously. Okay, move. So measuring latitude and longitude is a great example of how geography is partly a natural science and partly a study of human behavior. So let me give you the natural science. The natural science would be the lines of latitude, which essentially represents how far a place is away from direct sunlight. That's a very natural thing. We all experience the sun. But lines of longitude were a man-made creation, right? And you got to go all the way back to an English clockmaker by the name of John Harrison, who set his clock device that could keep time accurately on a ship. He set it to Greenwich, England, right? It's kind of close to London. Greenwich becomes the master reference time for every point on Earth. And what they do is they create, for every 15 degrees, a new time zone. For the most part, there's some exceptions to the rule. So for every 15 degrees, you move east or west, one will be entering a new time zone. 360, how many hours in a day? 24, you got it. 360 divided by 24 equals 15. So that's kind of how it works. Let me show you. Let's go to the United States. Okay, can we get to the United States? Here we go. Yes. There's essentially 4 main time zones in the United States. You have Eastern time, that's what we're on, Central time, Mountain West time, and West Coast time. Have you ever wondered, like, if you're trying to watch, like, prime time TV? Well, prime time TV on the East Coast is at 9 o'clock. Man, that's kind of late, dude. I'm trying to get up at 6 o'clock and seize the day. Well, why would they run it so late? Well, because what's the answer to 99 out of 100 questions? If you don't know this, learn this right here in this moment. The answer is money, all right? You want to have, if you're a TV show, right, those actors aren't in there, acting, for your benefit. They're getting paid. Well, how can they maximize their profit? They could do that by maximizing their access to the markets. So they run it at 9 o'clock on Eastern time because it's 8 o'clock Central time, because it's 7 o'clock Mountain West time, because it's 6 o'clock right when people are getting home from work in West Coast time. That's why, because everybody can have access to it and consume it, even though we're at different time zones, moving 15 degrees back at a time. Are y'all with me? Okay, good. Let's conclude this thing. GI science. GI science is the development and the analysis of data about Earth through satellites and other modern day electronic information and technologies. GI science uses what we call remote sensing. The basic idea of remote sensing is this: we're acquiring data from satellites. So remote sensing is acquiring without physically touching. Technically, if I look through a microscope and I'm not physically touching, that would qualify as remote sensing, or some binoculars, right? Actually, let me do that right. Some binoculars, that would qualify as remote sensing. If I'm putting my readers on, I think technically, if I'm not touching, that counts as remote sensing. But that's not, for the most part, what we're talking about. We're talking about satellite imagery. Okay, GPS. We use GPS to accurately determine Earth's position, our position in relation to the Earth. Now, I'm going to show you about all the satellites. There's 24 plus in predetermined orbits. I will show you a video when you get in class in terms of all this and how it works. We call this mathematic location. And GIS, Geographic Information Systems, I want you to write down layers. Layers are what we will call GIS. Essentially, you're taking one bit of information and layering it on another and layering it on another and making an informed decision about one's world. You can see a lot of complexity in GIS, right? I played baseball here at Southport High School, and we played baseball before it was renovated. We played baseball at Holder Field, which is at Mary Bryan Elementary School. Do you know why we play baseball at Holder Field? Well, what's the answer to 99 out of 100 questions, right? It's money. They got that land for cheap. Why did they get that land for cheap? Because it was built on a floodplain, right? And literally, there will be some times where we might only play 3 or 4 home games to hold the field the whole year because it was a heavy rain season and it just rained us out, right? All the time, we're getting rained out. But the land was cheap because it was built on a floodplain. So if I wanted to look at floodplains and then the price of land, I could see that the price of land drops when land is in a floodplain. Or I could look at transportation networks that are close to around there. And then I could look at businesses that are around. See, I can do a lot of stuff. Let me give you just one example of a place that I can go to use a GIS simulator. And that is IU does a thing here where this is an interactive GIS simulator. Hopefully you can see this. All right, so let's use some GIS. You can get to this website very easily, maps.indiana.edu. Okay, now, once you get here, you can look at different layers. We have demographic layers. We have environment layers, geology, government. There's some really cool things, right? So if you ever want to see like, hey, you know, I want to see, you know, the different congressional districts and where you're at, you can check that out. If you want to see, you know, voting districts, right? If you want to see, so there's some cool stuff there. So now, how could you use this to make an informed decision about your world, right? So it already gives us the counties and it already gives us the major interstates. Got it? Now, let's say, for example, I just want to look at, I don't know, let's look at child poverty, okay? Okay, we can see that there are higher pockets of child poverty here, and here. But let's see, you know, I don't know. I wonder if things are related. You never know unless you try. I wonder if in addition, so we still have our interstates, we still have our county boundaries. We are getting the pockets of child poverty using government data. Let's see where the agribusiness is located. Okay, so we can see all the different spots where there are agribusiness operations located. I don't see much of a correlation there, but you know, when I think of child poverty, I think of malnutrition. So maybe I just wanted to check out where the agribusiness operations were and their distance and price. See, this is layering data. This is just looking at things and seeing if there's a relation, if there's not a relation. And this is what GIS is, layers. Okay, so to review, how do the geographers describe where things are? Well, the first we talked about were maps. We talked about how they were historically tools for reference, but now they are more tools for communication. And then new technology. We referenced global positioning systems, GPS, GIS, aka layers, and this idea of remote sensing, which GPS would fall under the umbrella of, which essentially is evaluating without physically touching. Okay? All right, my friends, we hit our objectives. We looked at the differences between early maps and contemporary maps. We described the role of map scale and projections and making maps. We looked at latitude and longitude, absolute location, and we discussed some of the contemporary tools that we use. And look forward to seeing you in class. We'll make meaning with some of this. We'll get some project stuff going on. We'll really be able to work through a lot of this. Okay? See you next time.